Welcome back to part 2 of our SMPS Tech Training. Today we are talking about the regulator circuit. Alright, what we already see here in our picture is the regulator circuit of our switching mode power supply, which we are working on. And of course, we have seen already in part 1 that the regulator circuit is quite a little bit difficult, and we need to look into it to understand an SMPS entirely, right? So therefore, let's go back to our schematic first to determine where we have our controller circuit and what the controller circuit is doing. In part 1 of our video we talked about our high voltage part of our circuit, and we have not yet analyzed and determined what kind of circuit this really is. So that is what we will do when we start repairing. But now first we want to talk about here our controller and of course this connector down here, right? So that is important because we know if we have a load connected to our power supply, then of course the voltage will drop, and even if it is only a little bit, it will drop, and our regulator needs to control this voltage drop which we have at our output terminals. And the regulator has to make sure that the drop which happened, regardless how big this drop is, has to regulate it back to the wanted, in our case 13.5 voltage on the output terminals up to 22 amps, because we have seen that our switching mode power supply here on the bench is able to deliver 22 amps. And of course I agree with you, it looks really complicated, and even here, this terminal here, that is where we have our little vertical board on the main board, and then this operational amplifier and this thyristor, and of course our T2 is also part of our regulator circuit. And additional to that, to keep our regulator running right from the beginning when we have switched on our power supply by our main power switch, this little linear power supply has to jump in to supply our regulator circuit with voltage and current, just to be able to really start our switching process in our high voltage DC, high voltage part of our power supply. The controller board has different so-called arrow amplifiers on the board, and the arrow amplifiers are controlling different incidents, so such as what we can see here, for instance. So that is a temperature sensor which is controlling the heatsink temperature, and when the temperature rises a certain level, then the arrow amplifier gets the information, switch off our oscillation. Then, secondly, we see here on the board, for instance, a little LED, which is nothing else than an overvoltage protection. So we have seen in the diagram that there is a thyristor. Let's go up to our schematic. So we have seen here our V19, a little thyristor, and we have here our V16, so the red LED. And when we have, for any reason, an overvoltage, so that is caused by a fault, of course, then here our operational amplifier gives an high to its output, and it will switch on our little thyristor, which will then switch on our LED to tell us that there has been an overvoltage, and will then subsequently over our controller board switch off the oscillation which is necessary to control our high voltage part, so the switching part, if you will. And what you can see down there, so that here is a resistor, and that is an current shunt which is constantly controlling and, if you like, measuring the amps which are flowing through the output terminals in order to control the limit of the amps which can be delivered by our power supply, which we have here on our bench. And we have seen our power supply is capable for 22 amps, and of course if the current draw exceeds our 22 amps, then another error amplifier in our control circuit have to stop oscillating. Stopping oscillating means we are protecting our entire circuit and of course our high switching part, our high voltage switching part, and that is, as we already have seen it here on our schematic, that is of course our two transistors here and the whole high voltage part. So you see we have minimum already 4 error amplifiers, which is current, temperature, over voltage, and of course short. And maybe the designer wanted to control even more, so he is able of course to add additional error amplifiers to control and check for different parameters on our power supply. But in our cases it is most of the time this 4 parameters which will be checked, and if something is wrong, our oscillating will be shut down, and of course without oscillating our switching mode won't function. Okay, back from the error amplifiers to the shopper circuit, so how to run our SMPS power supply. So the main job, of course, of the SMPS controller is to run here our shopper circuit. So this is, as you might see, a flyback converter, and of course here's our transistor which is switching the coil here, and we need to switch it. To switch the shopper circuit is a pulse width modulator, PWM, to run the power supply. So you can see it here a little bit. So that is the whole power supply as a block diagram, and you see that we have here our inverter shopper and output transformer, our output rectifier, and of course then here, so that is the controller back to the inverter shopper. And we know, depending on the load at the output terminals, which are here, we need to give more energy or less energy into our power supply. and therefore we are using our pulse width modulator. So if we need more power, then here our diagram, so our pulses gets wider, and if we need less energy, so the pulses become more or less a peak, just a little peak, and that is indicating that we really need not much energy. In video 79, called Basic of Switching Mode Power Supplies, I have shown how this regulation works on a flyback converter. So if you have not yet seen video 79, it might be a good idea to watch it, because then you can see how the pulse width modulator works under real conditions. What we gonna do later on, we will do some experiments. So we will put a little circuit in place, and we build the pulse width modulator just to get a more deeply understanding how it works, and that will definitely help you to do your own probing on a faulty SMPS, of course. Alright, this is again a portion of the power supply we are working on, the schematic, portion of the schematic I mean. And you see we have here an operational amplifier, and we know that we have a board down here, a connector, where the little vertical board is on the main board, and there we have all the operational amplifiers, and we have of course here our driver transformer and such, and well, to get a better understanding what our amplifier or operational amplifier, regardless if it is this one or the one which is on the vertical board, works in general, we will dive a little bit deeper into that. I mean, this is not a training on operational amplifiers, so I hope that you already have worked with operational amplifiers, so therefore I do not go really deep in how an operational amplifier works, but we will get an idea what kind of operational amplifier we are working with, and what the expected function is. And therefore, just to get back to a basic schematic, so this here is a non-inverting operational amplifier. So it could be used for DC and AC, of course, so you have different possibilities to use an operational amplifier. In our case, it is more or less a DC amplifier, and you see our output voltage gets amplified by this formula here. So it is all about R1 divided by R2. So that will give us the amplification factor, and it is regardless if we do it with AC or DC, both can be amplified according this formula, and therefore it is the basic to understand what the designer has done in the power supply we have on the bench. And again, that is a portion of our real power supply, and you see that we have with C14 a capacitor in our signal pass. So, and the question here is, of course, what kind of function does this C14 have? And the answer is a little bit, if you look down here, so that is, if you like, this part here a little bit easier displayed. So we do have here our operational amplifier once again, and it looks like an inverting amplifier, and we have again our R4 and R3, which are determining the amplification factor, but then we have a capacitor within. And what we see here is our reference voltage, which we have here with our V18 as well. So you see that seems to be two very important parts which are used to control our shopper circuit, or controlling the load, controlling the output voltage. So, you know, here we have many different parts which are jumping in. And the PI regulator is obviously something which is very important. So we will have a look what our PI regulator is doing, and so that is a little circuit. And well, again, we cannot go deep into the operational amplifier function. I hope that all of you have already worked with it. Otherwise, you need to get yourself a little bit trained on that topic. But anyways, if we would not have our CI capacitor here in circuit, then it would be a normal inverting amplifier. So that is, I guess, relatively easy to understand. And according our formula of the voltage amplification we have seen in the other picture, we would get an output response from our operational amplifier, which look like this. We are talking about a square signal, which we put here at our input, or maybe we switch DC from 0 to high, or the other way around. So that is however it is designed. But anyways, I mean, this is an inverting amplifier, and that means our output response would go into the negative side. But anyway, so that is all not important right now. Important is that if we only have a P regulator, this is proportional. So that means if you switch your DC on, yeah, you have nothing here at the input, and now you put your DC on, then you would get the output response very quick to the maximum what our amplification factor is allowing. I hope that is somewhat clear. And so that is straightforward. Proportional regulator follows exactly, directly, according to its slew rate to the input. Okay. If we would not have our R2, if we only would have the C in our circuit, then we would have an what is it called? One second. So an integral amplifier, so an I regulator, and you see here the response. So we're doing exactly the same. We are using our DC, we switch it on, and according to the circuit design, you will see that our output voltage is following this output response. So you see it is going slowly up to the maximum amplitude which the circuit is designed to. And now when you have both regulators together, as we have it here, then you get, we're doing exactly the same, right? So we're switching on our DC at the input, and you see that now you get a direct response, so from the proportional part of our circuit. And then after our first response, then our I component jumps in, and it goes more slowly up to its maximum. And that is a very nice response, because of course if we have something happening at our output terminals, if the output voltage is dropping, right, then of course you need a very fast response of our controller. But on the other side, it should not be that quick and fast that our output DC at the output terminals is bumping back and forth. So that is not what we want. So we need, of course, a response which is quick, and that is doing our proportional part. But then we are going up to the maximum little bit slower. And that is because while the regulator is doing its job, the output condition could already have been changed once again, so that then of course the regulator needs to jump into once again. And I'm talking here about milli or maybe microseconds, where the regulator is really trying to get our output voltage to the right highs, that it really works as we want. And therefore our PI regulator is really a nice thing to do it. Okay, and now let's put our components together. So we have here our SMPS. So we have here our output terminals, we have connected our load, and what you can see here, we have our PI regulator. So we divide here the output voltage to needed voltage, because we need to get here all in a certain balance, and that is depending on the design. So it must be clear that all this needs to be calculated by the engineer who is designing this circuit. So the voltage here is depending on the used reference voltage, of course, and then it needs to get balanced that with the wanted output voltage, which is in our case 13.5 volt, is divided in a way that our PI regulator can work in the right way. So we do not dive deeper in that, but it must be clear that we need here a response if we have here a voltage drop. But on the other hand, even without any load, we need of course a driving signal here at the output of our second amplifier, and you see here that I have chosen here a second operational amplifier, which is in reality exactly what you can see it here. So we put here sawtooth generator to our operational amplifier, and with the response getting here out of our PI regulator, we will get here our driving pulses to our shopper circuit. And you see that, of course, even there is no load, we need here a driving signal towards our shopper circuit, and thus it might be getting more and more clear that this circuit really needs to be balanced, that everything works as expected, and that is in development the job of the engineer to get the setting, the presetting of this circuit according what SMPS type we are using, and which load the power supply is capable, and so forth and so forth. So you see how it might hang together. Okay, so let's have a little experiment on how we can build this needed pulse width modulator. And you already see here a little operational amplifier, which is representing nothing but a sawtooth generator. So that is what we have seen before, okay? And then how we can create out of this sawtooth generator the pulse width modulator pulse for triggering or driving our shopper circuit. So let's watch the signals on the oscilloscope. And first of all, I put voltage to our little test and experimental board, and let's see what we get. And here we have it. So that should be an sawtooth signal. I mean, it is not the most nicest what you can get, but it will work, and that is important for us. So that is what is coming out of our little operational amplifier. So nothing special, very easy design, and not sure if you can read it. I mean, it is not the needed 50 or 100 kilohertz which our normal SMPS is running on, but as I said, that is only a little test board, a little experiment that you see how it works. And now I switch on my second channel, because you see I have two channels here connected, and let's see if it works to see what we get. And yes, here we are. So what we see is that we have now a very nice pulse, and that pulse is at least the signal which will drive our shopper circuit. And as we have discussed it now several times, we need more energy in our shopper circuit in order to get more power to our output terminals, and we need, of course, less if there is no load or little load. So that means something what does not really draw a lot of current. Okay, so now what we see here on our scope could be the situation where our SMPS does not need to deliver a lot of power. So that means maybe there is no load connected to our power supply. When I now simulate that, when we now simulate that we get a load, it might look this way here. So you see now our pulse is getting wider, and that means we are definitely giving more energy into our coil, into our transformer, which is needed to be able to produce more power at our output terminals. And so if we have, for instance, a changing load, and think easily if we do SSB, an SSB single sideband transmission. You know that it is voice dependent how much power we bring to air. Okay, so and that is where this regulation, this pulse width modulation kicks in. So maybe when you talk you need a lot of power, so you have nearly a duty cycle 50-50, so 50% duty cycle of our square wave what we have here. And when we do not talk, then of course no output power is present at our radio output, so at the antenna socket, if you like, and so that would go down. Okay, and normal speech, it might look that it is doing that here, so that it is always delivering the right amount of power in order to be able to deliver the current needed to do the transmission. And going back here to our little circuit, so I'm simulating that with a little potentiometer, and what that means we can see here on our block diagram schematic. Okay, so that is what we developed before together to understand how our circuit, our real circuit where we are working on, works. And down below, that is our little circuit we did for demonstration, for our little experiment. And you see we have here our PART2 generator, and here a second operational amplifier, and that here is our potentiometer, and our potentiometer is connected to plus supply voltage and ground. So that means if we are moving here our potentiometer, we get more or less voltage to our positive input of our operational amplifier. And now to understand it a little bit better, depending on which point here on the PART2s we have our positive voltage here on our non-inverting input, our output gets created with smaller or wider pulses. And of course that is definitely what we can see here. And what I wanted to show you, because that might be important for troubleshooting as well, you have to watch documentations and data sheets of the components which are used. I have shown it in earlier videos very often that you need to look out for documentation of the needed, or not of the needed, of the used parts in an electronic device, and there you must have a look what the conditions are for the used regulator circuit itself, and on the other hand the design of the shopper circuit, because sometimes we are not allowed to go over a duty cycle of 50%. So for instance, if we would do our duty cycle, I don't know what it is now, maybe 80%, so the time where our transistor is switched through, or the switch, so we have explained it as a switch is closed, may lead to a malfunction, so you can destroy your transistor, or you can destroy different parts of your power supply. So that is something you must be aware on as well. So the most power supplies cannot handle more than a duty cycle of 50%. So it most of the time all happens from a very narrow pulse, which is under the condition of no load, or you are getting load and then it is varying over the time, which is for the respective circuit the right way to operate your shopper circuit. Okay, and I really hope you have now a basic understanding how switching mode power supplies working, how it hangs together, and that we really can finally start troubleshooting our faulty SMPS, which we have here on the bench, and we really can now use our knowledge, and we can follow what we have learned, and we will see if we can find everything what we have seen here in theory. Can we really see it here on our power supply? And that is what we are going to do in our next video, because I believe this is again many to overthink, and therefore if you put now this part 1 and part 2 of this SMPS videos together, we really can start troubleshooting and finally repairing this SMPS power supply. So see you next time, where we really put hands on and going to repair it. Thanks for watching, and catch you next time.